we have. Oh, sorry. This is recording. Okay, I just need to press here some button. Yeah. So as I was saying, so with future gravitational wave experiments, LISA, Einstein Telescope, Cosmic Explorer, and so on. Even today with LIGO, but it's a different physics purpose. We have there is this good opportunity to start also testing BSM physics beyond colliders or in combination with colliders, and this is one of the greatest motivations to look into new physics models, BSM models, also in the context of gravitational wave observers. Okay, so let me. So this is in this place here you can see Aveiro University where I work at the moment, and I'm working on the physics department, and also the research unit sits in the math department. Right. So as I was saying, the standard model is tremendously successful. And I would say actually boringly successful in terms of most of its predictions. But it fails in a few things that, from my point of view, are the four fundamental pillars to motivate the need for new physics. For me, one of the most important, and I think most of you agree, is that the standard model does not explain neutrino masses. And so we need to find a new theory, and there are, of course, many proposals to explain neutrino masses. This is one of the most striking ones. Also, dark matter is another unexplained phenomenological observation. We know dark matter is out there, but the standard model does not offer any explanation. There is another pillar for the need of new physics, which is the existence of baryon asymmetry in the universe. And the standard model, for instance, does not contain enough CP violation in order to generate the observed matter-antimatter asymmetry. And finally, there is one that I consider, this is my personal view on this, that is more on the not so. It's also phenomenological, of course, but also in a conceptual way, which is trying to understand the flavor problem. Why do we have huge difference in hierarchies in the fermion sector, both in the masses and the mixing? For example, why is the quark mixing hierarchical? Why is the lepton mixing not that hierarchical? Why is the top quark mass so much heavier than electron? And why are neutrinos so light? So all these questions are groundbreaking, and we need to find explanations for this. Of course, as I said, there are proposals for all of this, but the optimal solution would be to have one theory that could put all of this together. Of course, I could even come up with more things like the origin of the gauge couplings, which leads to unification, for example. And we could, of course, be here all afternoon thinking about other things that would also deserve an explanation. But so current and future experimental facilities will offer new and let me call multi-messenger channels to search for new physics. Multi-messenger in the sense that we can still use the collider channel, and actually the LHC still has a lot of data to deliver, at least one more order of magnitude than what was delivered so far in terms of luminosity. So there is still here a great opportunity, and also future colliders that are being discussed at the moment, from muon colliders to FCC to high energy LHC, as well as now LISA and the future gravitational wave observatories, where the hypothetical measurement of a stochastic gravitational waves background can give us information about new physics. There are other opportunities, other channels that I will not mention or very, very barely mention, which is, for example, experiments to look for the cosmic neutrino background, this CNB. There is this proposal, Ptolemy, which I found quite interesting, which can the purpose is to measure the cosmic neutrino background, and for example, it can really detect the individual neutrino masses through like neutrino capture on tritium, and then you measure like from beta decay, you measure the electron spectrum, and if you can see bumps on the neutrino mass in an energy corresponding to neutrino mass. So this is what I understood from a very, very brief read of this article. So if you want to know more, I recommend you to check this article here. Also, we also have cosmic microwave background experiments such as Planck that also can give us information about the early universe. Okay, now I will focus on the stochastic gravitational waves background, and this acronym will denote it throughout the talk, SGWB. And this stochastic background can emerge due to several components. And this is a huge, huge challenge, in fact. And a lot of work is needed in order to be able to distinguish between the various sources that can source the stochastic gravitational waves background. So on one side of the superposition of unresolved astrophysical sources, there was this recent article which is quite interesting, but also scary in the sense that these astrophysical sources are really a major component of this background, which can sort of block from sight, let's say in this way, other cosmological events. But of course, if you can model this, you can remove these backgrounds and start uncovering cosmological, so background from cosmological events. And these are, for example, from inflation, topological defects like the decay of domain walls, for example, cosmic strings, and phase transitions. And this is what I'm going to be focusing in this talk on the stochastic gravitational waves from phase transitions. And this is indeed, as I said, a good opportunity to probe new physics in combination or even beyond colliders reach. So in combination, if we can have an observable, and I will discuss a little bit about that, for example, the triple Higgs coupling, which can be detected or can be measured at colliders via di-Higgs production, or it can also enhance the strength of the phase transition and can be related to an hypothetical sign at gravitational waves observatories. But also beyond reach, colliders reach, because if we happen to find a stochastic gravitational wave background in a frequency much further above the frequency that would correspond to the electroweak scale, then we can be probing a region where the energy, so the mass, the characteristic mass, is really above the reach of colliders, like 100 TeV, 1000 TeV, which is within limit of future gravitational waves observatories, like the Einstein Telescope, for example. Right, so in essence, so what can we learn from future stochastic gravitational wave measurements, and which implications can we take for collider or high energy physics observables in general? So the current strategy, because at the moment we don't have yet gravitational waves detectors like LISA operating. So at the moment, what we do is we define our favorite model. We make predictions for the stochastic gravitational backgrounds, and then we look for collider observables, as I said, like trilinear Higgs couplings, scalar masses, and try to look for correlations between these observables and the ones that are important to generate a stochastic gravitational background. This is what we can do at the moment. But now let's travel a little bit in time to the future and imagine an optimistic scenario where we have LISA data, and we can do parameter inference from some signal that LISA can hypothetically see. Doing this parameter inference, we can start doing BSM model fits and or coming up with constraints on models in the same way that we do with colliders. And this can even give more motivation for colliders or direct us to where to find or where to look at colliders. In the same way that the existence of dark matter motivated WIMP searches at LHC, independently of we have not yet found any evidence for WIMP, and this paradigm is getting increasingly into some pressure. But we know that dark matter exists, and there is a motivation for WIMP searches at the colliders. So here, from this step 2 to step 3, it's exactly a similar scenario that I'm imagining at the moment. But we also can think of a pessimistic scenario where LISA is turned on, and then we don't see any stochastic gravitational background, either because they are too weak to be visible, or because the unresolved sources are really blocking us from seeing anything. So what we have to do is, at least we can put constraints on models, and we should keep going and trying to improve our understanding as we do these days with colliders. So this is a little bit the possible scenarios for the future. So now a little bit an illustration of the basics of phase transitions. So all of you know that there is so the standard model, for instance, the Electroweak symmetry breaking undergoes a second order phase transition, and here this is only an illustration, and I should give credit to my student Marco Finetti that did this nice picture. Notice here that there is this arrow which is the temperature. So where it's red is colder, and then it goes to this violet where it's warmer. So from right to left, it's heating up. But if we place ourselves in an early universe where the universe is very warm, so we have a symmetric potential, then it starts cooling down. And if we have a second order phase transition, it starts generating a minimum, or this, we can imagine this this as just a standard Mexican hat potential. But this is a crossover. Pretty much it goes directly from this minimum and smoothly rolls down to this to the new global minimum. But what happens if this is a first order phase transition? For the case of first order phase transition, imagine that we see it in a symmetric vacuum in the early universe. Now the universe cools down, and at a certain temperature we have here a critical temperature where a new minimum is generated with a potential barrier between the original minimum and the new minimum. Oh, sorry. Then the universe continues to cool down, and now the new minimum becomes deeper, so it becomes global. And at a certain temperature, the probability of nucleating a vacuum bubble per cosmological horizon becomes 1, and this is what defines this Tn, the nucleation temperature. And you start having these thermal jumps or transiting from one minimum to the others through this barrier, and this is a first order phase transition. At the end of the day, at some point, the universe percolates, and the percolation temperature is defined when all bubbles of this the new minimum are causally connected, such that the universe cannot go back to the original minimum. And this is what defines the percolation temperature. And this is the picture that we are looking for, because when this happens, it's when we can start generating gravitational waves. So another picture taken from this this article here, it's you generate these vacuum bubbles, then more vacuum bubbles are generated, they start expanding, and in this expansion, and depending on the characteristic of these bubbles, if they expand at the speed of light, which means they are runaway, if they don't have this terminal velocity, they can collide efficiently and generate gravitational radiation in the process. But typically, the friction of the plasma around it prevents them to reach this luminal velocity in their expansion, and they don't efficiently collide. But the sound waves generated in this expansion is the main source of gravitational radiation. There is also all this interference between the bubble fronts that generates turbulence, and which happens at somewhat higher frequencies, but it does not contribute for the peak of the gravitational waves, but for the tails. Right. So this is a picture of what we are looking for. Right. So how can we connect a particle physics model to these bubbles, let's say? There are a few quantities that characterize the phase transition. Its strength, the duration. For instance, these are the most important ones. Even the temperature, the percolation temperature, which is this T star. And if you see, so this alpha parameter, which is the strength of the phase transition, this is quantified in terms of this V, which is the potential. So in rough terms, we can say, so alpha is as strong as the vacuum energy, the difference in the potential energy. The larger the difference in potential energy between the true and the false vacuum, the larger this alpha. This rho gamma is the radiation energy density, which is given by this well-known expression here. And in fact, alpha, so the strength of the phase transition, is a ratio, basically in terms of this difference in vacuum energy over the radiation energy density. Another very important parameter is the duration of the phase transition, which is quantified by this beta over h parameter. This is inverse time, beta inverse, the inverse time duration in terms of the Hubble parameter. And the smaller the beta, the larger, the longer the phase transition lasts. So the longer time it's there, like sourcing energy. And which means that the larger or the more energy a possible stochastic gravitational wave will have. So to have visible gravitational waves, we want as large as possible alpha and as small as possible beta. Of course, this cannot be infinitely large, and this cannot be zero. Otherwise, we could this phase transition could take longer than the edge of the universe. That's not possible. And if this alpha is very large, we are in a super cooled regime, which can also be dangerous, because then we need to take into account also the details of inflation. We need to know if this would be in any conflict with inflation, and that's a whole different story that is beyond the scope of this talk, because in the models that I will be analyzing, this alpha is never too large, but large enough to make visible gravitational waves. So to compute this beta, for example, you need this Euclidean action, this S3 over T, which is defined here. And this S hat is actually the bounce, this is given by the bounce solution. And the effective potential that is in here that enters is where the particle physics information is stored, let's say, because you have here this V0, which is our model, it's our three-level potential. We also have a Coleman-Weinberg part, a thermal correction part, and also some counter terms here that are introduced in order to make sure that the Coleman-Weinberg does not destroy the physical minimum that we define at to V0. In other words, I decide in V0 what is the Higgs boson mass, and I decide where is the minimum of the potential. Then I put Coleman-Weinberg. You know that this will deviate it. This can destroy the Higgs mass, and this can deviate the minimum from the physical one. So this counter terms is to compensate for that and to make sure that we are in a physical minimum with a realistic Higgs boson mass. This is why we introduced this one here. Right, so these three parameters here, so the alpha, beta over h, and even the temperature, this is the percussion temperature, are calculated from a certain BSM theory. So we need to define our model in order to calculate these three quantities here. And these are used as inputs to obtain the gravitational wave power spectrum. So the gravitational power spectrum given by this is given by these two components here. One, which is the really important one, is the peak amplitude, and then there's a spectral function which gives you the shape of the stochastic background. It has sort of a Gaussian shape. But this is very important because this tells you the first, this blue, highlighted in blue, the peak amplitude, tells you how high is in energy density can the gravitational wave, the stochastic background be. And if you want you need to calculate this in order to understand whether a certain BSM model or a certain benchmark in a given BSM model can be probed by LISA, for example. So, and this peak amplitude, so it's written here, this is a function of the peak frequency. So actually the peak frequency to the power of -2 and a complicated function of alpha and t. And this, so here it's not important the exact shape of this, but this is just to show that that all these details that we need for alpha, so the particle physics information is stored here in this part, in this F. And the peak frequency is also a function of beta over h. So once again, both the peak frequency and the peak amplitude, they depend on the BSM model that we of our choice, and the certain point in particular, a parametric point that we may choose. So there are different proposals in the literature. So not all of them yet agree with the structure of this F, or more even in general of this omega in general. These formulas are obtained through our semi-analytical functions, and they are obtained from a lattice simulation. So there are the Helsinki groups. So there are a few groups, 2-3 groups working on this, and I think this is still there is still a lot of work to be done along these lines in order to converge to a better understanding. But at the moment, so in this work, I'll be using the formalism that is reported in the LISA cosmology working group papers, which you can check in this JCAP articles here. Okay, so after this a brief introduction of the details of this because of the phase transitions and gravitational waves. I'm going now to first scenario, and hopefully I will have time for a second scenario, which will be a lot shorter. But this is a scenario where we have electroweak and lepton-number symmetry breaking. So now we are choosing a specific BSM scenario. So this paper is this is the archive number, and it was done with this gentleman in collaboration with this gentleman here. First, let me set the stage for this model. As I said a few slides back, so LISA is sensitive to scales that go from the electroweak up to something which is more or less order 10 TeV. If we focus, because we can, of course, there are different models for lepton-number symmetry breaking, but we can choose to focus on low-scale lepton-number symmetry breaking. And low scale because we want to be somewhere close to TeV scale, so that we have a model that is a good physics case for LISA. And now we are going to look for neutrino seesaw models with a Majoron, but we need to choose which one. I will only consider 3 simple ones and choose one out of them. Based on the following arguments. So here I show you, so these are well-known models. So the first one, this first matrix is the well-known type 1 seesaw matrix with the Majoron. So these are models with the Majoron. So we have, so in this table of the SU2L doublet, you have right-handed neutrino. So we have this other sterile neutrino, we can call it sterile neutrino, and then we have the sigma is the Majoron, so this is a scalar, and this is the Higgs. And the U1L quantum numbers are written here. This cross means that, so in this type 1 seesaw model, we don't have this S. That's why this matrix is only 2 by 2, but in a block form. So this black bold, I mean, this bold matrices, Yukawa matrices are 3 by 3. Right, so this is the well-known type 1 seesaw. This is the inverse seesaw matrix, which corresponds to the charges here in the middle row. And we also have the extended inverse seesaw, which is this last line. The light neutrino masses are then given by these 3 expressions here. And now note the following. In the type 1 seesaw, we have this V sigma. So V sigma is the VEV of this of the Majoron, is in the denominator. For a moment, let's forget that we can also have hierarchies in these Yukawa couplings. But for simplicity, let's assume that the leading contributions to the smallness of the neutrino masses are coming from the mass scales in this problem. So for the type 1 seesaw, we want V sigma to be as large as possible. So we really go far away from the electroweak or TeV scale to get good neutrino masses. In the inverse seesaw, it's the same. So we want to have a large, maybe not as large, because there is a power of 2, but we want to have a large sigma VEV. And even it would help to have a small lambda, of course, in the limit of 0 lambda. We recover lepton exactly 1L, and the neutrinos become massless. This is well known in the inverse seesaw. So once again, the breaking of the 1L symmetry by this sigma wants to be at a large scale. It suggests to be at well beyond the electroweak or TeV scale. But if we go to the extended inverse seesaw, lambdas are now here in this off-diagonal part, and lambda becomes now in the denominator. So we want to have a large lambda, and nicely we have this V sigma in the numerator. So the U1L breaking wants to be at a low scale, and it can be not far from the electroweak scale. So this is the model the extended inverse seesaw, is the model that is well motivated to be searched for at LISA, because LISA is sensitive to scales around the electric one. As I said 2 slides back here, up to order 10 TeV, roughly. So from here onwards, we are going to focus on the extended inverse seesaw model. Of course, there are more neutrino mass models that we could further discuss. These are just the simplest ones to analyze in this aspect. Right. So this model was studied before. So in an article that we have done back in 2020. And we realized something there that was a little bit disappointing. That was this lambda sigma h, is portal coupling. So this is the Lagrangian. I mean, in this case, it's the potential of the Majoron model, the scalar potential. And it happens that this portal coupling here, in order to produce visible gravitational waves, you see that its value, needs to be about 0.13 or so. And unfortunately, this is too large because this induces too large. It's too large for invisible Higgs decay. So this induces a too fast Higgs boson decay into light Majorons. So this is not this scenario here is not viable if the Majoron, so this CP odd component of sigma is smaller than 60, about 60 GeV, smaller than twice the Higgs boson mass, saying 60 just roughly. So all the scenarios, all the nice scenarios where Majoron can be dark matter keV or can be electron volt. So there are many scenarios that are cosmologically interesting and see the Majoron as a light particle below well below the electric scale, are not viable or are not compatible with this picture because of this portal coupling. And having a too large Majoron, it's the only solution in this case. But and this is exactly, so this is just a little bit more details on what I have just said. So here we would need, in order to have, so if you compute the decay width of the Higgs into Majorons, and if you do this estimation, you need this coupling, this lambda JJH1, you need this coupling to be in order for this coupling to be to suppress the Higgs invisible decay. This translates into a bound on lambda sigma h of the order 10 to the -2. And as you can see in the picture here, this is 1 order of magnitude larger than what we need. Of course, you can say, okay, if maybe the model is still viable if the gravitational waves are well below the LISA sensitivity reach. Yes, that's true. The model, it's not invalid. It's still not observable. It's just not observable from this perspective. But we want to go explore a little bit more this. And we know that light Majorons are well motivated to be pseudo-Gaussian bosons. They are cosmologically relevant. And the point here is how to consistently modify the scalar sector and change this minimalistic picture. This is the minimal, the most minimal scenario that we can look for. Okay, once again, let's look into the neutrino sector, because this is so the motivation for what comes next starts here in the neutrino sector. So as I mentioned, so we are in this studying this extended inverse seesaw model, where we have three light active neutrinos with this formula that the mass are given by so the leading contributions are of this form. And we also have heavy neutrinos, which are essentially, their mass is essentially lambda. And so let me just mention this, highlight this lambda here, to say that this lambda, it's of an unknown origin at the moment. So this is here in this Lagrangian. So this is a heavy mass scale that we put by hand. But this is calling for some EFT approach, saying, okay, if this new physics scale is not really far from the electric scale, I mean, if it's a 10 TeV, 50 TeV, 100 TeV, something like that, perhaps an EFT approach to this problem is justifiable. And this is indeed what our proposal to address that the previous observation. Extend the theory with the 6-dimensional operators, U1L preserving 6-dimensional operators. So this orange part, this highlighted part here, are the extra operators. So these are here we have the h dagger h to the power of 3, h dagger h to the power of 2, sigma dagger sigma, and delta 4. So here delta 0 means that we don't have any power of sigma. Delta 2 means that we have 2 powers of h. Delta 4 means that you have, like, in fact, so you have sigma, 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 sigma. It's like four sigmas, and delta 6 is that you have 6 sigmas. It just to set up the notation here, so to understand the meaning of these deltas and the label 0, 2, 4, and 6. We still have all the other terms as before. I didn't mention there is also this soft term that was also there before, and this soft is a term that softly breaks the U1L symmetry, because U1L is spontaneously broken by the VEV of sigma, but then the CP odd component of sigma becomes a Goldstone, and with this soft term it becomes it's a pseudo Goldstone boson. So this is just why this term is here, because we want this to be the pseudo and non-massless pseudo Goldstone boson, basically. Right. So because we are in the EFT approach, we decided, so we want this lambda scale to be between 10 TeV and 1000 TeV, to be wide enough, but not. Of course, we don't want to make it all the way up to the gut scale, because then the EFT approach starts being less and less justifiable. And the interesting ingredient here in this 6D part is that now you have new portal couplings, in particular delta 2 and delta 4. And this delta 2 and delta 4 will allow the coexistence of LC invisible Higgs decay with, and at the same time, strong first order phase transitions. So we used, in order to make sure that our phenomenology is correct, so we use in our numerical scan, we use this the branching ratio of the Higgs into Majorons to be smaller than 0.18. So this is the most up-to-date this is from CMS, the most up-to-date observed, the upper bound on the observed decay branching ratio of the Higgs into invisibles. This is also the scalar mixing angle, so current constraints make it to be smaller than 0.23. This is also used as input, and also as input is the Higgs boson mass, as well as all these other parameters like the second CP-even Higgs mass, the Majoron mass, the VEVs. Okay, VH is 246. V sigma, which we want to be between electric scale and 1 TeV, let's say. The scale lambda that I mentioned before, as well as this delta 2 and delta 4 parameters. And now you see something here. This coupling here, the lambda JJH1, which previously was here. Let's see if I go a little bit back. So it's here in this decay in this decay right here. So this is what controls the invisible Higgs decay. Previously, it was only this component here. This alpha h is the scalar mixing angle. Let me just mention that. So now it's a much bigger expression, as you see here. It reduces to the other one in the limit of the 6D operators being 0, or in the limit of when lambda h is too big. It reduces to the previous expression. But you see now you have here a combination of parameters, and all these parameters, delta 2, delta 4, lambda sigma h, they don't need to be, they can be either positive or negative. So you will have some cancellation here, which is a mild cancellation. There is, it cannot even, it's not even a fine tuning. Of course, it's a tuning of parameters, but it's in the second decimal, first and second decimal tuning. It's really not a severe fine tuning problem by any means. And this is what will allow us to have sizable enough portal couplings, because having a sizable portal couplings means that the potential barrier between the true and the false vacuum is large enough in order to trigger strong first order phase transitions. If the potential barrier is too small, then the phase transition will be weak. But the larger the potential barrier, as long as you can have the transition, of course, you have a strong first order phase transition. You have more release of energy into the plasma. So these are just some inverted equations for some of the couplings. So this lambda portal coupling, lambda sigma, lambda h, and even this delta 6, they were not used as inputs. They were calculated from all the other inputs. So this is just to say that we have calculated them. And the information of the branching ratio here is in this ABR. ABR is this function that is here. It was just to simplify what is written above. Otherwise, it would be not possible to read. And this is all coded. And also, when you have all this information in, you should plug your information into the thermal effective potential. So you have the Coleman-Weinberg parts, as I mentioned before, and the counter terms here in blue, and you have the thermal part, which also includes this daisy resummation parts, in order to make in order to account for at high temperature to make sure that you don't break down perturbation theory. All right. Okay, so now let's come down to the results, to the juice of this presentation. Let's say these are our so the ranges of the scan. So as I mentioned, so you have the branching ratio of the Higgs into Majorons. We have here the scalar mixing angle. So here it should be 0.23, if I'm not wrong, not 0.24. So the E1L breaking wave, so this lambda scale, also the delta 0, delta 2, and delta 4, they are sampled, but they are sampled in such a way that these expressions here, so the effective coupling that they generate is perturbative, is within perturbative line. It can be very small, and also not larger than 4 pi. And this is sampled in an exponential way, such that you can cover all this range equally. Right. So here, this plot that shown up here is are the results that we obtained in the scan. We have a few more points below, but I just got the plot in the interesting region. So as I said before, you see alpha, this is the strength of the phase transition, which is given essentially by the vacuum energy difference, or the difference in potential energy between the true and the false vacuum. And you see that the larger the alpha, the larger the amplitude of the gravitational waves, as given by the blue violet colors on the laser region. So this red dashed line is the laser sensitivity curve. Also, beta of the parameter beta over h. So the smaller the betas, the larger the larger the amplitude, as I said before. Also, this line, these points accumulate in the line because this is a log plot, and if you take the log of this the peak frequency and use the expression that I gave above, you have here some value in the origin and a function of f peak, linear function of f peak with this slope -2 log 10. That's why you have this behavior, this accumulation of points in this way, plus some value which is let's say the value at the origin. Right. So another pair of plots here that gives also some interesting information is about this variation in the waves before and after the phase transition. So phi is h is when phi is h is the SU2L breaking wave, and sigma is the U1L breaking wave. So you see that this, let's call this the order parameter. This is also called order parameter, the delta VH over T star. And you see that to have signatures at LISA with a large enough signal to noise ratio, this is the signal to noise ratio, which is above 10, which is more or less what is considered to be in a region or where we can have a hope to see stochastic gravitational wave background at LISA. In order to have these large SNR values, you need also to have large values of this delta V over T. This is very well aligned with typically what you request for in order to have electroweak baryogenesis, for instance. You want this delta V over T to be bigger than 1. This is what quantifies a strong first order phase transition. And in the context of gravitational waves, typically it's this alpha that is the strength of the phase transition, but this is actually related to this delta V over T. Now, if you want to explore a little bit the structure of the potential of these 6D operators and the portal couplings, let me call in general all the portal couplings, the lambda sigma h, this delta 2 and this delta 4, you see there is more or less a symmetry along the zero axis here in these plots, which stems from the fact that this yellow shaded region here in this expression needs to be order 0.01. So you have, for example, delta 2 has some negative value, and delta 4 tends to have more or less similar positive value. And with the lambda sigma h, it can also be positive or negative, but they must conspire together in order to make this this coupling small enough such that the Higgs boson does not decay too fast into invisibles, into Majorons in this scenario. But also we see an interesting thing, which is this delta zero wants to be small, pretty much aligned with zero, in order to have visible gravitational waves. So this color scale is the peak amplitude of gravitational waves, and to be visible to LISA, let me go back for you to see. So this red dashed here, so you see it's more or less we want something more or less above 10 to the minus 14 approximately. Actually, along these lines it's even 10 to the minus 13 eventually. So going back down here, so this purple region here is the one that we are interested about, the one that is interesting in the sense of primordial gravitational waves. So we can focus on regions where delta zero is small. Even for sampling purposes, it's simple. We can just set delta zero to be small or even zero to make a cleaner study. And in this context, we have also studied three other important parameters. One is the scalar mixing angle, this sine alpha. The other one is the kappa lambda, which is the coupling modifier, the trilinear Higgs coupling modifier, and the second CP-even Higgs boson mass, the new Higgs boson mass. And what you see is that it's along this purple line, this purple band here, that we have most of the interesting points to be visible at LISA. And if it happens that in the light of this model, if we see some signature of a stochastic gravitational background, this will also favor this green band here on the on the right plot, which corresponds to a second Higgs boson mass centered in 200 GeV plus or minus 50. So this is in the light of this model, the most interesting region. Also, you see some shaded regions here. So the vertical ones are future are projections for the future constraints on the scalar mixing angle with 1% and 0.1% uncertainty. So the full line is 1% and the dashed line is 0.1% uncertainty. So you can really screen down even to further in to this central region of the plot. And the blue horizontal bands are projections for future high luminosity LHC and high energy LHC for the kappa lambda. So, for example, at the high luminosity LHC, imagine that we have now, we'll have in the future 1% uncertainty in the mixing angle, and we have full data of high luminosity LHC. So we will be restricted to this quadrant here that I'm highlighting now with the cursor, the same in the other side. Still, the values of the Higgs, the new Higgs boson mass, are well defined here to be more or less at 200 plus or minus 50 GeV here in the light of this model, of course. So this highlights the potential interplay between collider and stochastic gravitational wave background. And of course, we can make this, so this plot is well known, and this green band is corresponds to this to the bands, to that magenta band. So this magenta band here in terms of kappa lambda. So the various channels for di-Higgs production, and we can have some enhancements in some of these cross sections, in some of these. Some enhancements and some of them with not so for example this PP to top jet HH, it's actually damps a bit, but other processes like for example PP to TTHH, maybe we can have an increase, and PP to WHH as well. So it's just a matter of reading this this plot to see that we have some interesting prospects to interplay between collider and gravitational waves observatories in the future. From CMB constraints on this model, so one of the things that we can ask is, because we have Majorons that can decay into neutrinos, whenever the Majorons are heavier than neutrinos, of course, maybe we should also look into Planck data. But Planck data only cuts here a small bite on the parameter space, as you see here. So this is the region where you would have Majorons and thermalized with neutrinos. And this is excluded by Planck. And so this lambda J is given by, so it's J corresponds to a certain flavor, neutrino flavor 1, 2, or 3. and it's given by so mj over v sigma. V sigma is the VEV, the U1L breaking VEV. And here, once again, in the color scale is the energy density amplitude of the stochastic gravitational wave background. Also, to put in perspective, so if our majorons are lighter than neutrinos, they don't decay, and we have those scenarios. We were very flexible, so the majoron mass is flexible. It's pretty much not constrained. It's a free parameter in a way, but it can also be heavier than neutrinos, and it can decay. And here there are various, so all the scenarios where it decays are contemplated here. So this bite here, once again, is like due to the Planck data. But it's interesting to note that the nice points, the band where we have something that can be visible at gravitational waves observatory is marginally constrained here. So only the not so interesting points from a stochastic gravitational wave background point of view are slightly constrained here in this region of Morais majorons around 1 electron volt. Also, here I have, so this is the scale of new physics, and in the y-axis is the combination. So is this combination basically of Yukawa couplings, so that we have an idea of the suppression. What are the suppressing factors to provide neutrino masses? And here, of course, you see when the scale grows, we can also grow the size of these Yukawa couplings, and with lower scales, naturally we need to compensate that with a smaller Yukawa couplings. But this is the product of 3 Yukawa couplings. So individually, they are not incredibly small, but their combined effect is this is a log 10 scale. So their combined effect makes a big suppression in the neutrino masses. So this is just to put in perspective. There is not a clear. So basically, for every value of lambda, we can have visible stochastic gravitational wave background, but these two bands, the blue and the magenta band, are slightly, there is a slight offset between them, but it's not. But basically, there is not a specific scale that we screen out of here or something like that. Right. Okay. So just one question, Antonio. So how long do I have? I think I'm pretty much not having much more time, right? I had a second.
You can have 10 minutes more. It's fine.
Okay. So please, when I'm on the 8th minute, tell me so that I speed up. But I don't think I need more than that. So thank you. So this is just this was the biggest part of the talk, of course, and the conclusions of this part is that LISA is a promising endeavor to search for echoes of new physics, and observable stochastic gravitational wave background suggests a preference for relatively light new CP-even scalar around 200 GeV and a trilinear Higgs coupling modifier in this range that goes between 0 and 2. This is looking at those bands that I shown above. And it's interesting also to mention that it's possible, there is a future possibility to test and constrain multiple physical channels in various, so with various experiments, LISA, LHC, Planck. I also mentioned Ptolemy before, and we can move on. There are many more physics channels that, so we have some exciting times ahead in this sense. Okay, now I will want to report on some work in progress, because so far I talked about symmetry breaking at low temperature, and the question here is what if we wanted to talk about symmetry restoration at low temperature? This is a little bit exploratory at the moment. It started as just an exercise for fun, but now we are trying to understand a little bit better, and I will only report in some work in progress here. Okay, now I have a dark background because I stole this from an older talk of mine. Because when I'm talking about symmetry restoration here, let me put this slide again. Symmetry restoration. One example is SU3 color. We know that at zero temperature, SU3 is a preserved symmetry at zero temperature. But there is nothing that prevents it from being broken at high temperature, so at higher temperature. But what we need to guarantee is that even if there was color breaking at finite temperature, at low temperature, this symmetry must be restored. And so this is like the question, the physics question here, whether this is possible in a model. And one of the things that initially it was motivated by all the flavor data, and in a model with the leptoquarks that can undergo phase transition, some color breaking at high temperature if they get at finite temperature of F plus standard model. So it was a very simple model engineered initially for flavor anomalies. Now one of those anomalies is no longer there, the R kappa. But this model was built in that sense. And also, there was a UV inspiration for this model from unification principles, a flavor trinification model that I worked together with Roman Pasechnik and Werner Porod. So, and in this model, so these leptoquarks were naturally emergent there in this model, in such a way that proton was stable, so without proton decaying. So of course I'm telling all these details in this would be a seminar on its own, of course, but this is only to highlight some of the features of that model. So in that model, only this type of interactions, LQR, so QL is it's the type, so tilde is scalar. So if QR tilde is a scalar and the QL tilde is also a scalar, they can only interact with the lepton and the quark. So these Q tildes are leptoquarks and not diquarks. So we only have leptoquark interactions in that model, so there is no proton decay. But then it comes the question, of course, also this model was also engineered to explain neutrino masses. As we were talking about models for neutrino masses, this is another possibility where you don't have a seesaw mechanism and you have radiative generation of neutrino masses with these leptoquarks in the loop. So all the details are in this article here, and as well as in these references here, that older papers that were also analyzing this type of neutrino mass generation. But the point is that there is a rich scalar sector in this model, and we can consider the possibility that leptoquarks get a VF at finite temperature. And what I asked my student to do back a few months back was to classify all possible first-order phase transitions and determine whether we could have a stochastic gravitational wave background. So the first disclaimer is this is work in progress. There are still a lot of things to understand there, and the results are not final by any means. But at the moment, what we have is something like this. Maybe many of these points we'll discover that they are not consistent for one reason or another. Some breakdown of perturbation theory that was not properly accounted. So there are many things still being studied here. But what I want to point out is if you look into the vacuum structure at finite temperature and at zero temperature, you see, you find that all the points that have a black circle around are points where at zero temperature color is preserved. So these are healthy points from the vacuum point of view. All the points that don't have a circle around are points where at zero temperature you have color breaking. So those are not good points. Those are points to dump, pretty much. So the only viable points we found, so after classifying all possible phase transitions, it was found that we can have one phase that starts with one of the leptoquarks having a VF, and then the other leptoquark, which is the other leptoquark is a doublet, S is a singlet, R is a doublet. So the other doublet leptoquark and the Higgs, they don't have a VEV. Then you cool down and you restore the SU3 symmetry and break the SU2L symmetry. And you can also have a case where you have all the symmetries broken, and then you restore at 0 temperature, you restore only SU3 color. But most of the cases you have, you go from a phase where you have electric preserving and color breaking, and then you change the minimum around. So pretty much it flips. You go, the color is restored and electroweak is broken, and this is the pretty much the healthy in terms of vacuum configuration. This is the really, I mean, the one that is consistent. So all the good points so far are below Lisa. They've been approaching. This is a lengthy process, of course. On one side there is like it takes time to do this simulation, and on the other side we still need to understand a few details behind this calculation here. But I didn't resist in sharing these preliminary results here, which show this interesting flip between a color preserving and color breaking minimum. Okay, I will stop here. I think I used a little bit under this extra 10 minutes. So thank you very much, Antonio, and everyone for your attention.
Thank you very much, Antonio, for the very nice and complete talk. Question from the audience? Antonio, we had a question. In some of the plot that you show for the Electroweak Phase Transition, where you were plotting this kappa multiplier,
yes,
which gives you this deviation for the trilinear Higgs coupling with respect to the standard model, you consider value at about 10. What was exactly the maximum allowed value allowed by the 3 sigma range?
So please, yes, say, complete your question, please.
Yes, there is some, I mean, I think there should be some limit, but I don't remember by experiment, or certainly is very big for that case.
Yeah, so you're talking about the kappa lambda, right?
Yes, the kappa HH in one of the plot.
Yeah, exactly. So the currently, so the limits of the y-axis are the current limits. So the current constraints are here. It's up to 6.2 or something like that. It's the maximum, and the minimum is like up to 1.2, I think, or so this is the current bound. So that was your question, Antonio?
This one, and also I was wondering that why you were considering kappa lambda up to 6 if the experimental range is a bit lower, because I was a bit surprised that from larger than 2 will be outside the experimental range. For example, in your left plot. There is some reason for considering this kappa multiplier to 6, or just to show more parameter space?
Well, so this is, so this is what was obtained from, so you calculate this lambda H111 over the lambda standard model. And the thing is that this is calculated at one loop. And the one loop corrections can be quite sizable and make and basically modify a lot the kappa lambda up to like a few 100%. And this is actually what's happening in the next for larger values of sine alpha. That is what's happening, and it's the loop corrections there that are playing the major role. So there are two important comments here. One is that this is an estimation calculation. So this was done with the effective potential approach. So basically what was done is that you have the true level computation of the lambda HHH, which is trivial. It's just extracting the couplings. And then you have you take derivatives of the effective potential, and that way you extract the one loop contributions, you sum up with the 1/16 pi squared, and then you get this. So this is on an approximation. Of course, if you want to do it precisely, you need to go diagrammatically, and there are groups like from these guys from Hamburg, from Daisy, from Georg group, and so on. They recently released a package called NE3H or something like that to properly calculate it and in a momentum dependent way. Of course, here it's momentum independent. Here it's effective potential approach means that the external momentum is zero. So we are in the limit where external momentum is zero. But I was discussing with them at some point, and they even shown me some plots where they show that the effective potential prediction is kind of a line. It's a number. Like imagine 6. And then you have the diagrammatic calculation, and it gives something which is 5.5 or 6.3, something like that. So it's not a big difference in terms of precision. It would be important to that difference. It would make a big difference if you want to make a prediction for colliders. So you could not. It would be wrong using the effective potential approach. But in terms of this estimation and qualitatively knowing whether you have a big contribution or not, that using the effective potential approach is sufficient for that purpose. But this big, so I didn't choose this kappa lambda to be big. This is what came out of the calculation, Antonio. So if that was your question, and if I understood your question in detail.
Yes, I see that. Yes, this was the outcome of the computation. So
yes,
yes, and from this legion, only the kappa that are allowed are, I suppose, to this dashed horizontal line a bit larger than 2, right?
Yeah,
okay.
That's projection. Let's say at the moment everything here it's allowed with the current. So the current bounds allow all these values of kappa. The dashed ones. So you see the first dotted ones are the projection for the high luminosity LHC. This is the future. What is within this dashed is the future allowance. Let's say if imagine that unless you discover some Higgs at the LHC, and then you can say that kappa lambda is 3.5. But if you don't discover the projected sensitivity will give you this region in the within the dashed lines, horizontal lines. So this line here and this line here. Oops, sorry. So this is the projected one. So all the points above and below will be ruled out after the high luminosity LHC, let's say. If you even go to a high energy LHC, this is a high 27 TeV, then you can screen it down even further between these dotted lines. So you see, if these ones will even start touching and ruling out part of this magenta band, this interesting magenta band. So you'll be in a very narrow region here. But this is future projections. Currently, so all these points are allowed. So the dashed regions is future, what is expected for the future. And the same story for the mixing angle. At the moment, it's valid, everything that is below 0.23, the modulus of sine alpha, smaller than 0.23. So you see everything is allowed. But future measurements with more or with less uncertainty, 1% or 0.1% can screen down it to the a lot more, as you can see here in this plot. So this was to put in perspective. What we have now is everything in this plots. What we can have in the future is everything that is within these shaded regions, basically.
Thank you, Antonio. Thanks a lot for the very nice talk.
Thank you very much, Antonio, for the invitation once again and the questions. Okay.
More questions from the audience? If there are no more questions, we send the speaker again for the very nice and complete talk, and we'll be at the next seminar.
Thank you. Thank you very much, Antonio, and everyone for listening.
Thanks a lot, Antonio. Thank you so much.
See you. See you
Bye.
at a future opportunity. Bye-bye.
Bye. Bye-bye.